be honest with yourself for a second. Imagine you're sitting in your final Cambridge physics exam. The clock is ticking down, the tension in the room is palpable, and you're staring right at a massive 6-mark question on data analysis for syllabus 0625. Are you truly analyzing and recording scientific data? Or are you just scribbling numbers on a page, desperately hoping to pick up a stray mark so you can finish the paper and go home? There is a massive, fundamental difference between those two approaches. In the world of physics, and especially in the eyes of a Cambridge examiner, that difference is literally the line between guessing and knowing. It's the difference between an average grade and absolute mastery. Let's think about 2 types of students we see all the time. Let's call them Alex and Sam. Alex overloads their answers with raw physics facts, completely ignoring the data context, offering zero analysis. Sam, on the other hand, rushes. Sam doesn't read the command words properly and completely misses what the question is actually asking. Today, we're going to make sure you don't make either of those mistakes.
Welcome to this explainer. Today, we are diving deep into the exact step-by-step workflow you need to master physics data collection. We're specifically targeting the rigorous standards expected in courses like the Cambridge IGCSE. We are going to completely transform the way you look at a simple ruler, a stopwatch, and a blank results table. Because here is the secret. Top-tier students don't just memorize formulas. They level up their answers by understanding how data actually works. Every single paragraph you write, every table you draw, unlocks new insights and, more importantly, unlocks those higher grade boundaries. By the end of this session, you won't just be participating in lab experiments or blindly answering exam questions. You'll be engineering them. You'll be playing the game exactly how the examiner wants you to play it.
All right, let's jump straight into our game plan for today. We are going to follow a very specific chronological journey. First, we'll look at the purpose of data. Second, we're identifying variables. This is where we decode those tricky command words. Third, we are mastering measurement. Fourth, we'll tackle the absolute minefield of accuracy, precision, and errors. And finally, step 5, we'll be building the perfect table, which is guaranteed to secure you maximum marks. Let's start with section 1, the purpose of physics data. Before we even think about picking up a single piece of equipment or writing a single sentence, we have to understand the foundational why behind what we do in the physics laboratory. It's incredibly easy to look at data collection or a giant table of numbers in an exam paper as just busy work. But I need you to shift your mindset right now. Data is the absolute lifeblood of physics. Physics is fundamentally about explaining relationships in the physical world, and you absolutely cannot do that without recording highly precise measurements for analysis. These measurements, your data, are exactly what allow physicists to create the very equations you study in your textbooks. When an examiner asks you to interpret data, they are checking if you understand that relationship. More importantly, recording your data properly allows other people to check your work by repeating your experiments. Every single new idea in physics has to survive this rigorous process of repetition and verification. If your data is messy, your physics is messy. And before we continue and get into the real strategy, I need to remind you, subscribe to our YouTube channel AC Exams at acexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. It is absolutely crucial for staying on top of these strategies. Moving on to section 2, identifying your variables. It's time to define our moving parts. Before any experiment begins, or before you write down any answer, we must transition to the planning phase and identify exactly what we are working with.
So here's the crucial point where so many students drop easy marks. You need a strict, crystal clear understanding of the differences between what you change, what you measure, and what you completely freeze. Your independent variable is the one thing you, the experimenter, actively choose to change. You are in control of it. Your dependent variable is what you measure or observe as a result of that change. It literally depends on what you just did. For example, let's say you were stretching a spring, a classic 0625 exam scenario. The force or the mass you add to the bottom of the spring is your independent variable. The resulting extension of that spring, that's your dependent variable. Finally, your control variables are absolutely everything else. These are the factors you must keep exactly perfectly the same throughout the entire experiment to ensure your test is fair. If you don't control the temperature of a wire while testing its resistance, your data is garbage. Now think back to our student Sam, who rushes. When an exam command word says, state the variable that is kept constant, Sam panics and writes down the dependent variable. Don't be like Sam. Slow down, decode the command word, and identify your variables correctly before you write a single word.
Within those variables, you are going to be collecting different types of data. You need to quickly and accurately distinguish between qualitative and quantitative data so you know exactly how to structure your answers. Qualitative data is descriptive and non-numerical. It's about qualities,
Think about noting these specific names of different core materials used in an electromagnet, like iron, steel, or copper. That's qualitative. Quantitative data, on the other hand, is all about the raw numbers. It involves counting or taking specific physical measurements. For example, recording a drop height of exactly 2.0 meters or a swing time of 15.4 seconds. In Cambridge physics, quantitative data is the holy grail. It is what allows us to plot graphs, calculate gradients, and prove physical laws. All right, Section 3, Mastering the Measurement. Now we move from the planning phase to the execution phase. This is where we focus on the actual equipment sitting on your lab bench and how to use it without completely sabotaging your own data. This beautifully illustrates a massive trap that students fall into all the time, especially on the alternative to practical paper. When you have multiple measuring tools, like these two measuring cylinders that both hold exactly 40 cubic centimeters, which one do you actually choose? The golden rule of the physics lab is that you always look for the tool with the most spread out scale. Notice how the smaller, thinner cylinder on the left allows you to read the volume to the nearest 0.5 cubic centimeters. Now compare that to the wider one on the right, which only lets you read to the nearest 1 cubic centimeter. By actively choosing the tool with the more spread out scale, you are instantly giving your data much greater precision. It's a simple choice, but it shows the examiner you are thinking like a real physicist. And hey, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. We are dropping absolute gold like this all the time.
But listen to me carefully. Having the right tool is completely useless if you use it incorrectly. I want you to look really closely at this pendulum diagram on the screen. Whenever you are reading a physical scale, your eyes must be directly opposite or perfectly perpendicular to the reading mark. If you get lazy and look from above the line, your measurement is going to read too short. If you look from below the line, it's going to read too long. Failing to read at eye level introduces what is known in physics as a parallax error. This is a fatal flaw. It fundamentally throws off your data from the very first measurement you take. Imagine Alex writing a beautifully detailed 3-paragraph explanation of a pendulum's motion, completely unaware that every single one of their raw data points is ruined by parallax error. It doesn't matter how good your explanation is if your evidence is fundamentally broken. Always get your eye level right on the mark. Let's move to Section 4, Accuracy, Precision, and Errors. It's time to talk about dealing with variability. Because even with perfect technique, we have to transition to the inevitable, messy reality of experimental physics. Whenever you are in the lab or analyzing data in an exam, you are going to face two main enemies: systematic errors and random errors. You absolutely must know the difference. A systematic error is an error that skews your data by the exact same amount in the exact same direction every single time you take a measurement. Think of a top pan digital balance that reads 0.02 grams when there is absolutely nothing on it. Or think of a wooden ruler that has a worn-down, chipped gap before the zero mark. Every measurement you take with that ruler will be off by that exact gap. Random errors, however, vary in completely unpredictable ways. Here's a wild fact. The average human reaction time to a visual stimulus is about 1/4 of a second. So if you're manually clicking a stopwatch to time a fast-moving object, your biology is literally injecting random error into your physics data. Sometimes you click too early, sometimes too late. Now, here is the vital exam takeaway. Taking repeat readings and calculating an average will help minimize the impact of random errors, but taking repeats will do absolutely nothing to fix a systematic error. If your ruler is broken, measuring it 10 times won't fix the broken ruler. You have to recognize the error type to apply the right fix. Now, what's really fascinating here is the strict, undeniable distinction between accuracy and precision. People use these two words interchangeably in everyday daily life, but in the realm of Cambridge physics, they mean very, very different things. Accuracy is simply a measure of how close your recorded measurement is to the true, actual, accepted value. Precision, on the other hand, is about how closely clustered your repeated measurements are to each other, regardless of whether they are anywhere near the true value. Think of a dartboard. If all your darts hit tightly grouped together in the top left corner, way outside the bullseye, you are highly precise, but you have terrible accuracy. You can have highly precise measurements that are consistently completely wrong because of a systematic error. Precision is also directly indicated by the number of significant figures your instrument allows you to state. An instrument reading to 0.01 is more precise than one reading to 0.1. Understanding this difference is how you level up your analytical answers. Welcome to Section 5, Building the Perfect Table. It's time for the final reporting phase. This is where your raw, messy lab bench notes are transformed into a professional, scientific record that actually allows relationships to emerge. Designing a results table is a massive skill of its own, and examiners look for very specific things. Here is your pro tip blueprint for the perfect table. Usually, you should put your independent variable, the one you're actively controlling, in the very first column on the left. As you read across the row from left to right, you record your dependent variables. Furthermore, look incredibly closely at these headers. A perfect full-mark table header includes the variable name and the unit, separated by a forward slash. You write distance/m and time/s at the very top. Why? So that the actual working cells of your table contain absolutely nothing but clean, raw numbers. Sam, our rushing student, always puts 15s or 10m inside the table cells. That is a guaranteed way to lose format marks. Keep the units in the headers, keep the cells clean. Let's look at how this builds when we start processing our data. Step 1, you record your raw measurements accurately. Step 2, you calculate the mean from your repeated trials to reduce those random errors we talked about. But Step 3 is where almost everybody drops the ball. When you calculate an average or process data into a totally new value like speed or resistance, your calculated value cannot magically become more precise than your original raw data. If your raw measurements from your ruler only have 2 significant figures, your final calculated mean must be recorded to that exact same number of significant figures. Your digital calculator might spit out 8 decimal places, but physics demands you respect the physical limits of your measuring tools. When you are writing an analytical paragraph, maybe using the point, evidence, explanation, link, or appeal framework, your evidence must be properly formatted. Your point might be that speed increases, your evidence is the perfectly significant data from your table, your explanation links it to the formulas, and your link ties it back to the core question. That is how you construct a flawless, top-tier answer.
So we come right back to where we started this explainer. Every single time you step into the lab, or every time you open a Cambridge physics exam paper, you have a choice. Now that you understand the mechanics of independent variables, the absolute dangers of parallax and systematic errors, and the rigorous, unforgiving rules of data processing and table building, the question is simple. Will you treat your next physics challenge as a tedious chore to just get through? Or will you treat it as a precise, engineered quest for the truth? The data is sitting right there, waiting for you to unlock it. Use it well. And remember, students who implement these physics strategies see an average improvement of 2 full grade boundaries. But that only happens if they practice consistently with our weekly content. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to absolutely every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.